So this chapter, this section, we get into a little bit of the structure of the atmosphere with the goal of getting into weather, which will be probably later this week, early next week. All right, so the first slide there is just definitions of weather and climate. So kind of the main thing, the differences between weather and climate. Weather is short term. Especially living here in Indiana, we know that weather can change minute to minute, whereas climate is over a much longer period of time, a matter of years, tens of years, that sort of thing. I heard the comparison of climate is like your personality, where weather is more like your mood. So, I mean, your personality is not going to change quickly, but your mood can. So it's kind of similar, if that helps at all. All right, the next one, as far as composition of the atmosphere, I would star this one, highlight it, do something, whatever you do to draw attention to things that you should kind of keep track of. With composition of the atmosphere, the biggest component of the atmosphere that we're breathing all the time is nitrogen. It's almost 80%. And then the second highest is oxygen. So we need oxygen to survive. We have to breathe that to survive. Nitrogen, we don't need to breathe that to survive. But that is the biggest component of what we're breathing all the time. All right. A couple other things that are in the atmosphere that are of importance. Water vapor is really important because that goes into the formation of clouds, which you have to have clouds to have precipitation, so rain, snow, that sort of thing, which helps us for food. Also helps with temperature control of the Earth itself, which we'll talk about in a minute. And then ozone is kind of an interesting molecule. Most of the oxygen that's in the atmosphere is O2, so it has 2 atoms of oxygen. And most of the time, oxygen is really happy that way. Occasionally, certain things happen that form ozone, which has 3 atoms of oxygen. Ozone at higher altitudes blocks ultraviolet radiation, or some ultraviolet radiation, which helps us out. It's just one more form of protection that the atmosphere provides. Ozone at ground level is actually a lung irritant. It's a toxin. It's kind of a unique, unique molecule, unique compound, in the fact that it breaks carbon-carbon bonds, which not very many things do. So it's kind of nasty stuff if you have to be around it, but most of us aren't in the upper atmosphere where the ozone layer is. So, but overall, it's a good thing for us when it's high in the atmosphere. As far as pollutants, we're not going to talk about this one too much. Just the fact that transportation is the biggest source of pollution, of atmospheric pollution, and then the largest specific pollutant is carbon monoxide, which is a byproduct of internal combustion engines, and it's pretty nasty stuff. It's poisonous. It basically binds with the hemoglobin in your red blood cells, so your red blood cells can't carry oxygen. So it's pretty nasty.
So there's enough air in the world that doesn't kill you. Yes, I know there's a lot of cars that do that.
Yeah, I mean, there's the carbon monoxide that's produced by cars is dissipating out into the environment, so it's not really a risk, as long as you're outside. But in a closed environment, it's definitely very dangerous. So yeah, it's something to keep in mind. All All right. Next thing. Some of you may have heard the kind of the phrase or the kind of the terminology or whatever that the air is thin, or at higher altitudes, the air is thinner. That's basically just one way to say that at higher altitudes, there are fewer gas molecules that are there. So, fewer oxygen atoms or fewer nitrogen, there's just less up there. And that's because of gravity. So just like everything on Earth and in the air, the Earth is pulling all of that towards the center of the Earth. And even though gas molecules are really tiny, they're also pulled towards the Earth. So the closer you are to sea level, the more gas molecules there are going to be in the atmosphere. The higher up you go, the fewer there are. And then as far as atmospheric pressure goes, one way to think of atmospheric pressure is where you're sitting. Think of yourself as sitting in just like a plastic tube, and that tube goes all the way to space. If you were to take all the air in that tube and weigh it, that would be atmospheric pressure. It's the weight of all the air that's pushing down on it. So the higher you go up in altitude, the lower the pressure is. Because you can imagine if you're at sea level and the tube goes to space, you have this much, whereas if you're at the top of a mountain, you only have that much, so it's less. And like I said, there's less oxygen, there's less everything. So if you go up to higher altitudes, it's possible that there's not enough oxygen to kind of supply your body with the oxygen that it's used to. So if you're not used to it and you go up to the top of a mountain, you might feel lightheaded, you might feel like you're going to faint, those sorts of things. But your body will become adjusted over time. It just takes a while. All right, this next one, I would star this one as well. The fact that the atmosphere is divided into layers because of temperature and temperature changes. So it's nothing to do with altitude or anything like that. It's all about temperature and how the temperature changes within that layer. So the layer that's closest to the Earth, the troposphere, that's what we're in right now. The higher you go up, the colder it gets. So the temperature drops as you go up in altitude. When you cross into the stratosphere, that flips. So it actually starts to get warmer the higher you go up. Then when you get into the mesosphere, it starts getting colder again. And then in the thermosphere, it starts to get warmer. And then that's basically what takes to space. And then it gets cold and kind of weird in space as far as temperatures. But the reason we have the layers of the atmosphere where they're at is because of temperature. Like I said, I would star that, remember that, whatever you need to do to remember that. On that picture on the diagram, where it has the thing at the top left, where it says the aurora, kind of looks like, I don't know, paint smudges or something. That's at the altitude where the auroras form. These are just some pictures of that. The aurora borealis, which is the northern lights, and the aurora australis, which is southern lights. These are things that are phenomena that occur sometimes. They happen close to the poles, so the Earth, close to the North Pole and South Pole. It's kind of the same concept as a fluorescent light bulb. Inside a fluorescent light bulb, there's gas that's trapped in there. If you run electricity through it, then that gas becomes excited and it gives off light. The aurora is basically the same thing, except it's energy and radiation from the sun that excites gases in the upper atmosphere. And depending on what the gas is, it'll give off a different colored light. So it's pretty cool stuff. We'll talk a little bit more about it in the next couple of weeks. All right, so we'll go on the Earth. So the two main types of motion, not the only types, but the main types. The first one's rotation. So I have the globe here. So rotation. So the Earth rotates on its axis. Every 24 hours and some change, the Earth rotates once on its axis. That's 1 day. The other one, the other main type of motion is revolution or revolving. So if my hand is the sun, as the Earth goes around the sun, that's revolving. So that's 365 days plus some change to go around the sun once. I say some change because it's a little over that. That's why we have leap years every 4 years, is to make up that additional time. The next thing under Earth's orientation, I would definitely star this. This is one of those things that if you get 5 things out of the class, I mean, it doesn't matter if you get 104% or 32% in the class. If this is one of the things that you take away, it's a good thing. The reason that we have seasons is because the Earth is tilted on its axis. It has nothing to do with distance from the sun. It's not, oh, it's summertime, so we're closer to the sun. It's a really common misconception, but it's not the reason why we have the seasons. It's not because it's wintertime and so we're further away. It has nothing to do with it. The reason we have the seasons is because the Earth is tilted on its axis. In one of my grad school classes, they had this film from Harvard graduation, and they were asking Harvard graduates, I mean, they're in like cap and gowns and everything. They're asking Harvard graduates why we have the seasons. And they're like, oh, well, during the summer we're closer, and almost all of them were wrong. So if you just remember this, you're smarter than a Harvard graduate, at least in something. So the Earth's tilted at about 23.5 degrees. It changes a little bit here and there. And then you can have some big things like big earthquakes off the coast of Japan that actually shifts the Earth's axis and all that stuff too, but about 23.5 degrees. Depending on which hemisphere is kind of facing the sun with the tilt. So in this picture, the southern hemisphere is facing the sun, northern hemisphere is tipping away. The southern hemisphere is going to receive more direct sunlight. The angle that the sun's light is hitting the Earth is more direct. Whereas on the northern hemisphere, it's a more of an angle, so it's not as strong. So that's the big thing. It's all about that angle that the sun's light hits the Earth, and that happens because the Earth's tilted. So you can see, so here on the left, so here we have the northern hemisphere tipped towards the sun, and then as it goes around the sun, notice that it still stays tipped the same direction. It's just going around the sun that way. Here on the right, the Earth's tipped away, or the northern hemisphere is tipped away from it. Some important dates. You have the 2 solstices, summer solstice and winter solstice. So respectively, that's the day with the most daylight and the day with the least amount of daylight, and also the first day of summer and first day of winter. Yep.
So you probably can't answer this, because I'm sure a lot of people can, but in Indiana, you know how it gets cold one day and then the next day it's super hot. Why is that?
It's just weather patterns.
Is that because of the tilt, or because you said like, my guess is like when it tilts and it's going around, it's tilted farther away from the sun, that's why it's winter, correct? Or
For us, yeah, when the Earth's tilted away from the sun, that's winter for us in the northern hemisphere. So because the seasons are flipped. So whenever it's summer for us in the southern hemisphere, it's winter. When it's winter for them, it's summer for us. But as far as weather, like, you know, hot one day, cold next day kind of thing, it's just where we're at and where we're located in the US. You know, where we're at, especially, you know, kind of this time of year, it's still really easy for cold air to dip down from Canada in the Arctic. And then it's really easy for, you know, warm air to come up from the Gulf of Mexico and things like that. So it just varies. That's also, and we'll get into this later, but that's why we have so many storms, is because you have cold air coming from the north and you have warm, moist air from the south. And when you have mixed cold air and air that has a lot of moisture and warm,
then the sun doesn't
It
get
drops.
warmer or colder, doesn't, the earth doesn't move closer, or, so it's like,
yeah, it's just weather patterns and wind patterns and things that give that kind of daily change. But we're in a really good place for that weird stuff to happen. On these autumnal equinox and the spring equinox, if you're at the right latitude, you can have 12 hours of daylight and 12 hours of darkness. We're not there, but places on Earth do have that. So again, that same diagram, you can see, so if the summer solstice on the left, where it's summer for the northern hemisphere, and again, that would be winter for the southern hemisphere. And then as the Earth progresses, we're at the fall equinox or the autumnal equinox. So you have equal day and night. Then we're on to the winter solstice. So the least amount of daylight, it's winter for us. And then on around to the spring equinox, equal day and night, and then on back to summer. So it's just kind of an up and down as far as the amount of daylight that we have. So like right now in April, each day is getting a little bit longer, or there's more daylight by a few minutes. And then once we hit June 21st, 22nd, then every day there'll be a little bit less. All right, a couple of definitions. Heat and temperature. So heat's just the transfer of energy from one thing to the next. And then temperature is the measure of the kind of the energy within something. And there are, you know, a few different types of thermometers that we use to measure temperature. And then this diagram in the bottom right shows some equivalencies as far as temperature goes between Celsius and Fahrenheit. Which, you know, looking at this, you can kind of see why the metric system makes sense. Water freezing at 0 and boiling at 100 instead of freezing at 32 and boiling at 212. It just doesn't make much sense. There are only 3 countries in the world that don't use the metric system, and we're one of them. So, so as far as conduction of heat and conduction of energy, 3 ways that transfer, or 3 ways that can happen, is conduction, convection, and radiation. This is a pretty common example. This kind of, you know, hand holding a pot of boiling water, because it does include all 3. So the first one, conduction, is through direct contact. So that's the kind of the quickest and most effective way of energy transfers through conduction. You know, so if you touch something hot, you made direct contact with it, that's conduction. Next one, convection. So transfer from molecule to molecule in a fluid. So a gas could also be considered a fluid as well, because it does move and flow. But in convection, just like in the convection currents in the mantle, hot things rise, cool things sink. So like in the pot of boiling water, as water's heated up at the bottom, it's going to rise to the top of the water and then cool a little bit and sink, and then, you know, up and down. It's the same reason, you know, hot air balloons float. Same reason why, you know, upstairs is going to be warmer than a basement, all that. And then the third is radiation. which is the transfer of energy through electromagnetic waves. The really nice thing about radiation is it can happen in a vacuum. It can travel through space. If that weren't the case, we wouldn't be here because we wouldn't be able to get the energy from the sun, which we need that. We need that for plants to grow, so we can have things to eat. You have to have that, so it's a nice thing. As far as electromagnetic waves go, and the electromagnetic spectrum, visible light is a very small portion of that spectrum. It consists of what we call white light, which can be broken down into the spectrum. Sometimes that happens naturally, like in a rainbow. Other times you can do that at will with a prism. And this just shows, a pretty good representation of the electromagnetic spectrum. Like I said, notice that the visible light portion is really small compared to everything else. Things that are higher energy tend to be more dangerous. And the higher the energy, the more dangerous it is. So ultraviolet radiation is, it's dangerous. I mean, it can, cause cancer, that sort of thing. X-rays, even more dangerous. Gamma rays, even more dangerous. Those are things that you don't want to be around. And then as you go into the lower energy, different types of waves, infrared. Infrared is just basically heat. So if you have an infrared camera, it's going to pick up heat. Or if there's an infrared lamp, it's just a heat lamp. You get in microwaves, TV, radio, that sort of thing. Those are things that are not going to damage you. Another thing with radiation is the wavelength of the radiation that's given off by something depends on the temperature of that thing. So I'm sure we've all seen like a stove element. As it heats up, it changes colors. It goes from that just kind of like dull black brown color to kind of a dark red, then a brighter red, and kind of an orange. The reason that it gives off different colors is because it's a different temperature. So it's giving off, has a different amount of energy in it. So it's giving off a different wavelength of light. And we've learned over time that, if you see a piece of metal that's giving off some sort of color, it's probably best not to touch that. Typically bad things happen. And here are a few pictures just from some thermal imaging cameras that were kind of cool. A volcano, and then a dog. You can see the highest temperatures are where the blood vessels are close to the skin without any fur or anything. And then that bottom right, what?
The dog or whatever.
Mm-hmm.
The ears and the face.
Mhm.
Is that the hottest? Or
Yeah.
is the yellow?
The white parts are the hottest.
Okay.
Yep. And then that bottom right with the the race cars. I mean, they're driving around the track it says 182 miles an hour. So the bodies are relatively cold because 182 mile an hour wind is going to cool off pretty much anything. But if you look at where the heat's coming from the engine compartment, the wheels, and you can even see the heat radiating off the track itself. I thought it was kind of cool. Not because I'm a huge NASCAR fan or anything, but it's kind of a cool picture. All right. Whenever radiation hits something, three things happen. So part of it's absorbed or taken in by the object, part of it's transmitted, so it goes through it, and then part of it is reflected, so it bounces off. So the example of clouds, when sunlight hits clouds, some of it's absorbed by the clouds itself, which heats up the clouds. Some of it's transmitted, so some of it goes through the clouds, which I can vouch for that because one of the worst sunburns of my life was on a cloudy day. I couldn't feel how hot it was, but it was pretty awful. And then some of it's reflected. So this is one of the ways that clouds affect global temperatures and local temperatures, is because they reflect sunlight and that energy back into space. Reflection and scattering, a couple of vocab words. We're all pretty familiar with reflection. I'm sure everyone has at least looked at a mirror at some point today, some more than others, I'm guessing. Light comes in at one angle, leaves at the same angle, angle of incidence equals the angle of reflection. Pretty standard stuff. Scattering, similar but a little bit different because it does exactly what it says. It scatters. So, light energy or radiation, hits something and it's scattered in different directions. Clouds are really good at this. The water vapor that's in those clouds are good at scattering light energy. And then the last slide is the greenhouse effect. So one thing, greenhouse effect and global warming are not the same thing. Greenhouse effect can contribute to global warming, but they're not the same thing. Basically, greenhouse effect is when clouds or certain gases in the atmosphere trap heat that would normally be reflected back into space. Yeah, let me finish this up. So some of the radiation and energy and heat from the sun hits the surface of the earth, bounces off the earth, and where it would normally go into space, it's trapped either by clouds or certain gases like carbon dioxide, and then it's reflected back down and it heats the earth up a little bit more. It's the same concept as a blanket. A blanket keeps you warm because it traps your body heat. So you're essentially heating yourself. So it's basically the same thing. It's trapping that energy, so it keeps warming the earth a little bit. All right, does anyone have any questions? Any slides I need to go back to?